My name is Jürgen Neugebauer. I'm happy to chair the session, and I'm also happy to give the next presentation. I'm a professor on the University of Applied Science in Austria since more than 12 years in the moment, and since 2016 I had the chance to lead a research project dealing with thin glass. And in my presentation, I would like to speak about adaptive facade systems made from thin glass. Yeah, the motivation, why? Why I would like to deal with the thin glass? I would like to show a movie of an exhibit I did in the meantime 5 years ago. It was exhibit on the fair trade in Düsseldorf, a movable canopy. And that is a perfect example to start the presentation because it's an adaptive system. You can see how it works. Many thanks once again to the company who sponsored this exhibit. And the movable canopy, you can see it here in the, let's say, in the width of more than 3.5 meters, total height more than 4 meters, made from thin glass, laminated safety thin glass, 2 times 0.7 millimeter glued with a normal PVB together, linked together with hinges to a steel rod, and yeah, can be closed and open. And the basic idea behind was that in the States there is traditional to have the national anthem in front of every sport event, and if it rains there are a lot of umbrellas, and that could be used instead. If it rains, the national anthem can be sung, and then it goes back and the game can start. Why thin glass? Why I'm so involved in this thin glass? So I would like to show you a picture. That's a romantic picture, isn't it? But on the second thought, that's a picture made in Greenland a couple of weeks ago, not far away. There should be ice or snow, yeah? And therefore thin glass. And I would like to show you a graph made from a scientific group in the same building. I have my laboratory 3 stories above me, and they made this data evaluation, climate data evaluation, and the prognosis to the future. You can see here the prognosis to the future is there is a ramp in the temperature, climate change +2. In the meantime, we have 2019, we're on the level of +1.06. And if you remember Paris, the Kyoto Protocol, we have to limit it is 1.5. This intention failed. I can assure you this failed. We have to think about what's happened if there is a +2. Yeah? Maybe one answer is the thin glass. And another, more nicer motivation is the behavior. It's crazy, isn't it? I was 15 years in the glass business as a structural designer. Every time a limit of stress, a limit of deflection. Of course, now also a limit of stress, but about the deflection, we can discuss about this. Okay, that leads me to adaptive systems. Yeah, why adaptive systems? If I see the big majority of facades worldwide, they have 3 tasks. Separate the interior to the exterior, hamper the heat flow from in the winter inside to the outside, in summer outside to the inside. And the third task is hanging, boring 25 years and waiting for the demolition. That's enough. There's nothing else. So therefore, adaptive system. A facade should make more, harvest energy, play with the sun reaction, and so on. There are so many activities a facade can do. And one is the adaptive system. This facade is called adaptive facades. They can be influenced by the environmental surrounding impacts and play with this. Yeah? And how can we describe adaptive system a little bit more? If you have adaptive system, you can say there's a user-controlled adaptive system. To describe it with an example is very simple. If it is warm inside, you go to a switch, make a click, a small window opens, and that's an adaptive system, a controlled adaptive system. But there are other kinds of adaptive systems, autonomous adaptive systems. And these autonomous adaptive systems, you can also divide it in two different kinds. Indirect autonomous adaptive system and direct autonomous adaptive system. Let's start with the indirect autonomous systems. You have a sensor. You can measure the temperature, the humidity, the light, and so on. Create an electric impulse, goes to a control system. The control system transfers this information, maybe with an intelligent algorithm, to another impulse, and this other impulse gives the signal for an actuator to do anything. Yeah? Directly, or you can, if you think about movements, you can use also a multiplier in between to have a small initial movement and at the end a big movement. And the last one, the direct autonomous systems. The benefit of this is, in comparison to the indirect autonomous systems, they don't use electricity. There's no control system inside. For example, if you use, I come later on, a B-method method, they can make the movement directly in dependence with the dependence on the temperature. Yeah, so we have the inference from the environmental, so the temperature, the light, the humidity, and that leads, let's say, a change in the facade. For example, a movement, the glass can bend, or a change in the view through the glass. The glass change from transparent to translucent, or a change in the state of aggregation, the triangle between solid, liquid, and gas state. That's adaptive. Give me two examples for the view. So I think on the right side, everybody knows electronic glass. You put electricity on it and it's switchable from transparent to opaque and so on. On the left side, let's say a direct autonomous system, thermotropic interlayers in the glass with this nanocapsules that changed the state with the heat, and then the glass became from transparent to translucent. And with the change to the translucent, there is a reduction of the heat transfer from the outside to the inside. That's adaptive. If we think about movements, at first we have to see which kind of movements we can create. So we can bend the glass in one direction. We can bend with the curvature in both directions. We can roll it. We can twist the glass. Yeah? There are so many possibilities to create movements in the glass. But there's one basic we have to fulfill. All these types of glass have to be developable. What means developable? Yeah? One explanation is dealing with the so-called Gaussian curvature. What is the Gaussian curvature? A mathematical description of this is you have a geometry. You can create a normal vector on this in every point of this surface, and you can create flat surfaces which includes this normal vector, and you find the maximum and minimum curvature. That means the intersection between these flat surfaces and the curved surface. And if you multiply this minimum and the maximum, you will receive the Gaussian curvature. It's pretty easy. And there are so many programs which this analysis is installed. With a click, you can receive the analysis, as you can see here on the right side. The curvature can be positive, that's like a balloon. Negative, that's a membrane structure, or zero. And if it is zero, then you have a developable surface, and that is what we need. A much easier explanation is every surface you can create with a sheet of paper is developable. I think this explanation is much easier. Yeah, if you would like to start the movement, you need actuators. And from the kinematic side, you see two possibilities to have a movement of a point. Translation along a line and the rotation. And all other movements are combination of these both principal things. So therefore you have to, it's much easier to see the actuators, linear actuator, actuator which rotates, and the rest is a combination. If you go to the side of the direct autonomous actuators, you have, for example, the beam method. Yeah, you combine two methods with a different thermal expansion, and with the heat, there's, let's say, a curvature in this and that direction. You can use this for initial movement of a certain point on the glass surface or an edge of the glass surface. Another possibility is to use the humidity instead of the heat. Yeah, you have this B-wood system with a different behavior due to humidity. Then you have receive also a curvature. Or another example is the so-called shaped memory alloys. Yeah, you have an initial state, then you can cool it. It becomes another configuration, then you can force it, it becomes a deformation, and if you heat it once again, it goes back to the initial configuration. And that is a repeatable circle you can play with. And with this you can start an initial movement, and then comes the so-called multiplier in the game. And the multiplier, for example, here, a system of levers. And you can see here very good, the right side, the point on the right side, the red one, has a small movement. And if you go here, you can see what happens with the system. A small movement here, a big rotation here. You can see here, as a summary of the previous slides, a small movement of point C and the big movement of point A and B. And this could not be flat, this could also in the 3D space be done. Yeah, for what applications can we use such systems? The first application, you can use it for energy harvesting. This idea was motivated by a project realized a couple of years ago from Sheila Kennedy from MIT in Boston. He has some, let's say, stripes on the roof with a thin film inside embedded, and this sheets of glass followed the sun from the south orientated from the east in the morning via the south to the east to the west in the afternoon. And the same can be done with such example here in this slide here. You have a normal rectangular shape. Then you have bowed the glass a little bit, and if you have a rotation around the midpoint, you can play with the geometry of the glass, and with this small movement, like this and that, you can rotate the glass and follow the sun. The next one deals with let's say the temperature, for example, by a double skin facade, to play with the so-called chimney effect. If you need more fresh air, we can open it on a certain point of the facade. This can be also done autonomous with, for example, a B-metal stripe makes an initial movement, and the rest can be done by, let's say, by the glass or the multiplier in it. The next one is to deal with the sun, a daylight control system. That was a master thesis of a student of mine. He had a project in the middle of Manhattan, a skyscraper, and a double skin facade with the, let's say, the design of triangles. And he divided the triangle from bigger to smaller, 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 and so on. And one element you can see in the next slide is a triangle which open and closable elements made from glass. And the idea is you have different angles of the sun in the morning, at noon, in the evening, and with the let's say different geometries of the glass, you can handle the angle of the, let's say, the reflection of the sun on the glass surface itself. You can see here the mock-up my student did, not made from steel and glass, made from timber and plastic, much cheaper. And you can see here this triangle shape, the triangle design, and in the middle, surrounded by these white strips, there is the openable and closable system. How it works: on the right side you can see a small sketch. You introduce a little force on the bottom. With this introduced force, you have a small movement on the bottom, like 20 millimeters. And with a connection to the midpoints, marked here with the point B, there's a small movement inside. Yeah? And you have a small movement inside. There have, let's say, an influence of the shape of the glass. Yeah? And this influence of the shape of the glass, you can see here in the next slides, very easy. You can see here the closed situation. And with the movement inside, this glass opens and can be closed as well in the other direction. Okay, I say that I keep the time very well. That gives the possibility for questions. Are there any questions? Yeah, they're in the background. Peter, if I see right.
Hey, Jürgen. Very good presentation. Thank you very much. How is this stable in the wind condition? How are you keeping this in the position when you need to keep it in the position, and then when you open it?
Yeah, if I go, can I go back also? Yes. So here, I think I can explain it with this very well. The sides are supported with the steel rods, a flat metal, the straight lines. Then you have the hinges together. Then you have the benefit of, let's say, a little bit familiar with the folding system. You have two different surfaces linked together, and they are stiff in all directions. The weakest point I can see is the middle, the end of the glass. Maybe you have to stiffen it with, let's say, a small frame. But this, I had the piece of glass of this in my hand, a laminated safety glass of 2 × 1 millimeter. And for this application, with the size around like a little bit more than 1 meter between these two horizontal lines, that was definitely too stiff. In the meantime, I think that we need, let's say, less thickness for this application. Or you have to increase the surface of the glass. I have the feeling Peter has an additional question.
Yeah, so what is the force, what you need to move it then? I think, is it not too big?
No, it's not really big. I think that was around 5 to 6 kilonewton. And that's very easy for a motor device like this.
Yeah, it's 500 kilos.
Yeah, that's not that much. Yeah. Thank you.
Hi there. Did you like what you just saw? If you did, why not like the video? Drop us a comment below, as well as share the video with others, since GPD is all about sharing. And to receive more videos in future, subscribe And don't forget to click the bell icon for notifications. Ciao.